So, we are discussing about the fuzzy neural network, fuzzy min-max neural network for pattern recognition. And in the last class, we have said that how the hyperbox classifiers can be extended to a fuzzy min-max neural network, where every middle layer node in the fuzzy min-max neural network will compute the fuzzy membership function of an unknown point to a particular hyperbox. Then outputs of all the hyperboxes belonging to the same class, they are gathered together in one of the output layer nodes or class nodes, where the class node decides about what is the maximum membership given by the different hyperboxes belonging to different classes, and the membership function to that class is this maximum membership of different hyperboxes belonging to the same class. So, if I have C number of output neurons pertaining to C different classes, then every C neurons will give me a membership function, and this membership function is the membership of the unknown feature vector to the corresponding class. Okay. And we said that this itself can be taken as fuzzy classification, because this is nothing but a membership vector, or if we want crisp classification or hard classification, then whichever neuron gives the maximum membership value, we can put the unknown feature vector into the corresponding class. So, we can have a max operator which will give us a binary vector, where only one of the components of the binary vector will be equal to 1, and that obviously corresponds to the maximum membership, and all other components of the binary vector will be equal to 0, and that is equivalent to our hard classification. Okay. So, today what we will do is we will take the same example that we have taken for designing the hyperboxes. Okay. And we will take the same example and we will redraw the hyperboxes, and simultaneously we will try to design a fuzzy min-max neural network. Okay. So, this is nothing but learning or training of the fuzzy min-max neural network. Okay. So, the set of points that we had taken in the last class is something like this. We had taken a point having the components 0.7, 0.7, and we said that this belongs to class 1. Okay. And let us simultaneously draw the hyperboxes that we will get out of these points that we have taken. Okay. So, we will do it like this. The lines are very light. Okay. So, I will put it like this. This is 0.1, 0.2, 0.3, 0.4, Okay. So, when we said that this point, this feature vector 0.7, 0.7, this belongs to class 1. So, immediately we said that there will be a hyperbox for which the min point and max points are same. Okay. So, I will have a hyperbox somewhere over here 0.7, 0.7. Okay. So, at this location I will have a point hyperbox for which min point and max point is same, okay, that is 0.7, 0.7. And for this hyperbox, let us try to generate this fuzzy min max neural network. So, as we said that I assume that there are two classes, class 1 and class 2. So, obviously, in the output layer I will have two nodes, one corresponding to class 1 and other one corresponding to class 2. Okay. So, the first node corresponds to class 1 and the second node corresponds to class 2. Similarly, at the input layer also I will have two nodes, because I am considering feature vectors of dimension 2. So, at the input layer also we will have two nodes. Okay. So, I have node 1 and input node 2. Okay. And this will have the input feature vectors. And while designing this fuzzy min-max neural network, what we have to do is we have to generate three matrices, because from the middle layer to the output layer the connections are actually binary connections, either 0 or 1. 1 means there is a connection from a middle layer node to the corresponding output layer node. 0 means there is no connection from the corresponding middle layer node to the corresponding output layer node. And I will have two matrices which represents the connections from the input layer nodes to the middle layer nodes, and those two matrices actually represent the min point and max point. So, for min point I will have a matrix U, for max point I will have a matrix W, okay. And for the middle layer node to the output layer node I will have matrix V and W, not U and W, V corresponding to the min points and W corresponding to the max points, and I will have a matrix U which represents the connections from the middle layer nodes to the output layer nodes. Okay. So, if I use this convention that for every node in the input layer I will have one row in matrix U and one row in matrix W. Okay. So, this matrix V and matrix W. So, matrix V will have two rows corresponding to the min points, and the number of columns will actually be variable, because till now I do not know what is the number of nodes in the middle layer. Okay. So, the number of nodes in the middle layer, that will actually represent that how many columns I need in these matrices V and W. Okay. So, matrix V will have two rows, similarly matrix W will also have two rows. Similarly, for matrix U also, let us assume that we will have two nodes. I mean, it depends upon which way I represent the matrix. Okay. So, here in matrix U, a row will correspond to one of the nodes in the output layer node, the other row will correspond to the other node in the output layer node. Okay. So, from input layer to middle layer, a connection V I j will represent a connection from ith node in the input layer to the jth node in the middle layer. Okay. Whereas, in matrix U, the entry U j I, okay, will represent the connection from the jth node in the middle layer to the ith node, a connection from U j I will represent a connection from the ith node in the middle layer to the jth node in the output layer. Okay. Or I just said the reverse, jth node in the middle layer to the ith node in the output layer. Okay. So, accordingly, for every node in the output layer I will have a row. So, in these matrices what I have to go on adding is the number of columns. Okay. So, for the first point that we have considered, this point is 0.7, 0.7. Okay. So, min point and max point they are same, right. So, accordingly, in matrix V I will have to introduce 0.7, 0.7, because that is the min point. Okay. Similarly, matrix W I will have to introduce 0.7, 0.7, because that is also the max point. Okay. And I have to introduce one node in the middle layer corresponding to this particular feature vector 0.7, 0.7. Okay. So, the corresponding entries in matrix V and W I have already established, and it is known that this feature vector belongs to class 1. Okay. So, as this node belongs to class 1, so the corresponding column in matrix U will be 1, 0, indicating that this node is connected to C1 only, this node is not connected to C2. Okay. Similarly, when I consider the second point that I have is point B, which is 0.75, 0.75, and this belongs to again class 1, right. So, coming over here 0.75, 0.75 is this point, this also belongs to class 1. So, I generate a hyperbox, assuming that this expansion is permitted, I generate a single hyperbox containing these 2 points. Okay. So, now find that the earlier min point and max point that we had generated, this min point and max point gets changed, and I am not introducing a new node in the middle layer, only the min and max points I have to change, and because I am not introducing any node in the middle layer, so the matrix U will remain unchanged. Okay. So, what I have to do is over here the min point is now minimum of these two. Okay. In the first dimension, the minimum of 0.7 and minimum of 0.75, it remains 0.7. Similarly, minimum of 0.7 and minimum of 0.75, it remains 0.7. Whereas the max matrix, that will be maximum of these two. Okay. So, it will be 0.75, 0.75, right. So, the matrix W, though initially we had set it 0.7, 0.7, now it will be 0.75 and 0.75. Okay. So, any time the min point and max point gets changed, I have to change the corresponding entries in matrix V and matrix W. Okay. Now comes the third point. The third point that we considered was point C, which is 0.9, 0.9, okay. And we said that this point belongs to class 2. Okay. So, I will take this 0.9, 0.9 over here. So, 0.9 and 0.9 is this one, okay. And this belongs to class C2. So, obviously, I cannot expand any of them to include this particular point, and this is the first point, the first feature vector that is considered from class 2. Okay. So, naturally, I have to introduce a new node in the middle layer, right. So, I introduce a new node in the middle layer, and as I know that this hyperbox will belong to class C2. So, this will only have a connection from here to C2, it will not have any connection up to C1. So, accordingly, the corresponding entry in matrix U will be 0, 1. Okay. Now, I have to set the entries in the other two matrices, that is V and W. Okay. And you find that this is the only feature vector considered so far belonging to class C2. Okay. So, naturally, its min point and max point will be the same, and min point, max point, both of them will be 0.9, 0.9, okay. Max point will also be 0.9, 0.9. Okay. Now, I consider the third point, where the third point is D, and it is 0.8, 0.8, and this also belongs to class 2, right. So, corresponding to this, I have 0.8, 0.8 somewhere over here, and suppose I can expand this hyperbox to include this also. Okay. So, the new hyperbox that I will get is this one. Okay. So, now in this hyperbox you find that the max point will remain the same as the previous hyperbox, whereas the mean point has to change. Okay. So, earlier the mean point was also 0.9. Now, the mean point has to be minimum of these two. So, it will now be 0.8. Okay. So, earlier this 0.9 which we had put, this mean point has to be 0.8. Okay. So, now let us take the fifth point, which is E, and the vector is 0.1, 0.1, and we said that this feature vector belongs to class 1. Okay. So, for this I will have the hyperbox at 0.1, 0.1, right, and suppose that this hyperbox belonging to class 1, I cannot expand to include this. Okay. So, I have to generate a new node for this hyperbox, and that new node I have to generate over here, and as I know that this belongs to class C1. So, the corresponding entry in my matrix U has to be 1, 0, okay, indicating that this node belongs to class C1, right. And then I have to make an entry into the matrix V. I also have to make an entry into the matrix U, into the matrix W, and here again, because this is a point hyperbox. So, the mean point and max point, they will remain the same, that is 0.1, 0.1, here also it is 0.1, 0.1. Is that okay? So, then let us consider the other point, that is point F, whose coordinates are 0.2, 0.2, and this point also belongs to class 1, right. So, over here this corresponds to 0.2, 0.2, a point somewhere over here, and assuming that this point 0.1, 0.1 can be expanded to include this point, I get a single hyperbox, and this single hyperbox belongs to class C2. Okay. And because I am not adding any new hyperbox, okay, so I do not have to add any node. The previous node that I have, only in that node I have to change the mean point, max point. So, accordingly, I do not have to make any entry into matrix U. In matrix V and W, I have to change the mean point and max point. So, the new mean point that remains minimum of these two. Okay. So, the mean point does not change, but max point has to be maximum of these two. So, the max point has to be changed to 0.2, 0.2 from 0.1, 0.1. Okay. So, the new max point that I get, earlier it was 0.1, 0.1, now I have to make it 0.2, 0.2. Okay. The other matrices remain the same. Then let us take the next point, that is G, where the vector is 0.3, 0.3, and this belongs to class 2. Okay. So, 0.3, 0.3, if I put over here, 0.3, 0.3 comes at this location. Okay. So, you find that this belongs to class C2. The earlier hyperbox for C2 was this. Assuming that this cannot be expanded to include this, so I have to add a new node in the middle layer. Okay. So, the new node in the middle layer comes somewhere over here. and I know that this belongs to class C2. So, it will only have a connection to C2, the classifying neuron C2, and accordingly the corresponding entry in the U matrix will be 0 1. Okay. So, this is U matrix. Now, this is a new node. So, and a point hyperbox. So, I will have the mean point and max point, which is same as 0.3, 0.3, max point will also be 0.3, 0.3. Okay, the same mean point, max point. Then you come to the next point, which is 0.15, 0.15, and this also belongs to class 2. Okay. Coming over here, 0.15, 0.15 is this, right? And assuming that I can expand this to include this one, so the new hyperbox that I will generate is this one. Okay. So, this becomes my new hyperbox. And now we find that this one is hyperbox belonging to class C2, this is hyperbox belonging to class C1. So, whenever I have such a situation, because there is an overlap, I have to break these two hyperboxes. Okay. And to break these two hyperboxes, I have to find out that in which dimension the overlapping is minimum. So, here you find that along the horizontal dimension, the overlap is, this is 0.15 and this is 0.2. So, the overlapping is 0.05. In this dimension, it is 0.15, this is 0.2. So, in this dimension also it is 0.05. So, in both the dimensions, the amount of overlap is same. So, I can break this hyperbox in any of the directions. Okay. So, let us assume that we break the hyperbox along the middle of the first dimension over here. So, when I break this, I get two hyperboxes. One hyperbox is this one, which belongs to class C1, and the other hyperbox is this one, which belongs to class C2, right. Now, over here you find that when I am breaking these two hyperboxes, I am not generating any new hyperbox. There was a hyperbox corresponding to this, and there was a point hyperbox corresponding to this. So, it is the point hyperbox which has been expanded to include the second point, and while it was expanded, there was an overlap. Because of this overlap, I had to contract this hyperbox. Okay. So, what I have to do is, I have to change the mean point, max point accordingly for this hyperbox, which was a point hyperbox earlier. I have to change the mean point and max point for this, which hyperbox was already existing, right. So, what will be the new mean point, max point? For this hyperbox, the mean point remains the same, right. What is the max point? Max point is this coordinate, right. And what is this coordinate? This coordinate will be 0.15 and 0.2. Sorry, yeah, max point for this hyperbox will be 0.15, 0.2, right. So, this is 0.15, 0.2, and that is the max point of this hyperbox, the modified max point. Okay. Similarly, the mean point of this hyperbox, which is nothing but this location, okay, this will be 0.15 and 0.15. Okay. So, 0.1. Pardon? Oh, right. Earlier it was 0.15. So, now it will be 0.175. 0.175, and this will remain same as 0.15, right. And this is 0.175 and 0.2. 0.175.2. Okay. So, the max point of this hyperbox is going to change. Okay. And for this hyperbox, earlier I had a point hyperbox for which the mean point and max point was same. Now, the new mean point will be this, max point will remain unchanged. Is it okay? So, coming to our V matrix and W matrix, you find that for the earlier one, where the mean point was 0.1, 0.1, okay, and max point was 0.2, 0.2. Now, the new max point is 0.175, 0.2. Okay. So, this 0.2 now gets replaced by 0.175. The other point, the other dimension, it remains as 0.2, right. For this one 0.3, 0.3, which was a point hyperbox, for this point hyperbox, the max point remains the same, okay, but the mean point becomes 0.175 and 0.15. Is that okay? So, the mean point will be, for this will be changed to 0.175 and 0.15. Is it okay? Now, let us take the next point. The next point is I, for which the coordinate is vector is 0.45, 0.45, and this belongs to class 1. Okay. So, for this I have 0.45 and 0.45, this belongs to class 1. Okay. And suppose this cannot be included in any of the hyperboxes after expansion. So, I have to make a new node for this particular point, whose corresponding to which the vector is 0.45, 0.45. So, I generate a new node, and I know that this node belongs to class C1. So, accordingly, I have to make a connection from this node to class C1, and correspondingly matrix U will be modified as 1, 0. Okay. And I have to enter the mean point and max points in these two matrices, and because it is a point hyperbox, so the mean point and max point will remain the same. So, both of them are 0.45, 0.45, here also it is 0.45, here also it is 0.45. Okay. So, when I consider the next point, that is point j, corresponding to this the feature vector is 0.5, 0.5, and this also belongs to class 1. Okay. I come over here 0.5, 0.5, that is this, okay, and assuming that this point hyperbox can be expanded to include this, so I generate a new hyperbox. And because I am not adding any new node, because the previous point hyperbox has been expanded to include this, so U matrix will remain the same. However, I have to look at the V matrix and W matrix, and here you find that the max point that is being changed. So, earlier max point was 0.45, 0.45, now the new max point is 0.5, 0.5. Okay. So, I have to change this corresponding entry in matrix W. So, it will be 0.5, 0.5. Okay. Then let us consider the next point. The next point is K. The feature vector is 0.42, 0.42, and this belongs to class 2. Okay. So, I come over here, this is 0.45, 0.45, okay. 0.42, 0.42 will be somewhere over here, somewhere over here I will have 0.42, 0.42. And assuming that this has to be a point hyperbox, I have to have a corresponding node in the middle layer. Okay. So, I have to have a node in the middle layer, and as I know that this node belongs to class C 2. So, I have to change the corresponding U matrix, right. So, I have to make a column, add a column in the U matrix, which will be 0 1, because this belongs to class C 2. Okay. And in the U matrix V matrix, I have to generate, I have to add a column corresponding to this particular point. Okay. So, this is 0.42, 0.42, here also it is 0.42, 0.42. Okay. Then I take the next point. The next point is 0.55, 0.55, and this belongs to class 2. So, according to this, I have over here 0.55, 0.55 somewhere over here, and assuming that this can be expanded to include this, I have this new the modified hyperbox, which comes like this. And now you find that there is a containment. Okay. So, because there is a containment, I have to contract this hyperbox. So, this new hyperbox will be contracted. Let us assume that we contract it from this location. Okay. So, on this side I have one hyperbox belonging to class C 1, and on this side I have another hyperbox belonging to class C 2. Okay. So, over here you find that this hyperbox was already existing, and for this hyperbox the min max point has not been changed. Okay. So, accordingly the earlier entry in our matrix V matrix and W matrix, that remains the same, that is 0.45, 0.45, 0.5, 0.5. This remains unchanged, right. Whereas, for this new hyperbox, okay, I had earlier the mean point, which is 0.42, 0.42, that corresponds to this particular point. And when I have expanded this to include the second point, and because of this expansion there was a containment, and due to this containment I had to contract this hyperbox. Okay. So, as I have contracted this hyperbox, the mean point has now changed from here to here, right, and this is my max point. So, what is this new mean point? The new mean point is 0.5, 0.42. Okay. That is the new mean point, and the max point is 0.55, 0.55, 55 and 0.55. Okay. So, accordingly I have to make the modification over here. Now, the mean point becomes 0.5, 0.42. Okay. So, this will be 0.5, 0.42 as it is, and the max point, which earlier was 0.42, 0.42, because it was a point hyperbox. Okay. Now, the new max point will be 0.55 and 0.55. That is this one. Okay. So, this max point, new max point becomes 0.55 and 0.55. So, with this I have included all the training points that were given. So, at the end of the training, the three matrices that I have generated are like this. Okay. So, I have this U matrix which represents connections from the middle layer nodes to the output layer nodes, and I have two matrices V and W corresponding to min points and max points of the nodes which are generated in the middle layer. Okay. So, I over here these are represented by the matrices V and W, and over here the connection is represented by matrix U. And I have the final memberships computed to the two different classes C 1 and C 2, which comes from the output layer nodes. Is that okay? So, you find that your network has been trained in a single pass, unlike in case of multi-layer perceptron or single layer perceptron. What we have done is, we have changed the weight vectors or the weight matrices iteratively. Every time a given feature vector becomes misclassified, then following the gradient descent approach or following the back propagation learning, we had to change the weight matrices for different layers. And once it is changed, I have to recheck with all the samples, all the feature vectors which was used to train the neural network before this. That means, I have to come to a conclusion that the multi-layer perceptron or single layer perceptron has been trained properly only when in a pass all the samples are correctly classified, all the training samples are correctly classified, or the error that you get is less than certain specified value or less than the tolerable value. So, the training algorithm of the neural network in such case was an iterative algorithm, whereas in this case the neural network is trained in a single pass. Okay, because every time what I am doing is, if there is an overlap, I am immediately contracting the existing hyperbox, which takes care of the fact that there is no overlap or no ambiguity during classification or during testing. Okay. However, as we said before, that the problem with this fuzzy min-max neural network is that as we are going for contraction. Okay. So, here you find that say this point, which we know that this belongs to class C 2, but because of overlap and contraction, finally this point has been classified into class C 1. Because now, if I after this contraction operation, if I present the same point to this neural network, the neural network will say that this point belongs to class C 1, though I know that this point belongs to class C 2. Similarly, for this, I know that this point belongs to class C 1, but after creation of these hyperboxes and contraction of these hyperboxes, if I present the same point to the neural network, it will say that this point belongs to class C 2, though I know that this point belongs to class C 1. Okay. So, that is the disadvantage of this kind of neural network, and such a kind of problem you get both over here and over here. Because earlier we know that this point belongs to class C 1, okay. But after creation of these hyperboxes and contraction, now if I present this point to the neural network, what it will do is, this for this point it will try to calculate the fuzzy membership function to this hyperbox and also the fuzzy membership function to this hyperbox. And now you find that this point is nearer to this hyperbox than this hyperbox. So, the fuzzy membership function for this hyperbox will be more than the fuzzy membership function for this hyperbox. So, naturally, if I go for hard classification, this point will be classified to this class C 1, though we know that it actually belongs to class C 2. Okay. So, after this expansion and contraction process, you see that the training samples which are used to train the classifier, train the neural network, those samples themselves will be misclassified, or some of those samples themselves will be misclassified. So, naturally, due to this contraction, we are introducing some amount of error in our learning process or in the training process. Okay. So, we have suggested some modification to this kind of algorithm, that is by introducing the concept of compensatory neurons. So, what we have done is the basic structure or the classifying section of this neural network called reflex neural network remains the same as what has been suggested by Patrick Simpson, that is fuzzy min-max neural network. Okay. So, in the new architecture, I have, as before, a number of classifying neurons in the output layer, okay, a number of input layer neurons, let me draw on another paper. So, I have a number of classification neurons, I have a number of input layer neurons, is same as the number of classes that we are considering. The number of input layer neurons is same as the dimensionality of the feature vector that we are considering. Okay. So, the major part of this reflex fuzzy neural network is same as the fuzzy min-max neural network which has been suggested by Simpson. Okay. And we have this middle layer nodes which are basically hyperboxes. Okay. And as we have just seen that these number of nodes in the output layer and the number of nodes in the input layer, they are fixed by the problem, whereas number of nodes in the middle layer that we create during the training process. Okay. And accordingly, we generate matrix U, matrix V and matrix W. Now, what we have suggested is, we have suggested two more sections in this neural network, which is called the compensation section. And in compensation section, again, as we have just seen, that we can have two types of situations. One is overlap situation and the other one is containment situation. And the kind of compensation that you have to impart is different. In case of overlap compensation, we have to give some sort of compensation. In case of containment, we have to give some other type of compensation. Okay. So, accordingly, this compensation section that we have generated, this compensation section is again divided into two parts. One of them we are calling as overlap compensation, the other one is called containment compensation. Okay. So, I will have some additional nodes, one in the overlap compensation section, this we call as overlap compensation, and the other one is containment compensation. So, what is done in this overlap compensation and containment compensation? Whenever there is an overlap, like here, while training, if we find that there is an overlap, in the previous case what we have done is, we have contracted the hyperboxes to remove that overlap. Now, we do not go for contraction, but we go for gradation of the membership function within that overlap region. Okay. So, whenever there is a overlap, a new node is introduced in the overlap section. Okay. So, over here in the overlap section, we will introduce a new node . Okay. And this new node will give one compensation to the classifying neuron corresponding to this hyperbox and another compensation to the classifying neuron corresponding to this hyperbox. Okay. Because I cannot grade the membership of only one hyperbox, I have to grade the membership of both the hyperboxes. Okay. Because if a point falls within this region, in the overlap region, normally our classifying neuron in this section, classification section, both of them will give membership to membership function of 1 to this class and membership function of 1 to this class. Okay. I have to modify both of them or compensate both of them. Okay. So, this new neuron that we are introducing in the overlap compensation section, that will actually generate two outputs. One output is meant for compensation of one class and the other output is for compensation of the other class. Okay. So, if I have class C I and class C j, the hyperboxes belonging to class C I and the hyperboxes belonging to class C j, they overlap. Okay. Then output of the compensation neuron, that will give compensation to both C I and C j. However, amount of compensation to C I and the amount of compensation to C j will be different. The reason is, if this point is nearer to this point, then the membership function to C I to C j should be more, and if this point is towards this, then the membership function to class C I should be more. Okay. So, the amount of compensation that you give to class C I and the amount of compensation that you give to class C 2 or C j, they cannot be same, they have to be different. And while calculating this compensation values, you have to take care that to which of the points your unknown point is nearer. Okay. So, what we are doing is, in this section also I will have a number of classifying neurons or compensation neurons, which is same as the number of classes that I have. Okay. This will get output from the input, this will get input from the input layer neurons, and output of this will actually go to two of the output layer neurons, because I have to compensate for ith class as well as for jth class. Okay. Similarly, in the containment section also, I will also have a number of output layer neurons, which is same as the number of classes that I have. Okay. Here again, whenever there is a containment like this, I will put a containment compensation neuron. Okay. Now, why I said that the amount, that the type of compensation that I have to give in this case is different from the type of compensation that you have to give in this case, is that here I said that I have to compensate the outputs, the membership functions of both class C I and class C j, right. Whereas, in this case, if any feature point lies over here, we are saying that it should get a membership value of 1 to this class, whereas the membership value to this class has to be 0. And my hyperbox in the classifying section, that itself will compute membership value of 1 to this class. It will also get a membership value of 1 to this class. I have to make the membership value to this class equal to 0, and the membership value to this class should remain unchanged. That means, I have to only compensate the membership value of one class, which is containing the hyperbox of another class. Okay. So, the hyperbox that is contained, the membership value of that should not be changed. However, the hyperbox which contains the other hyperbox, the membership value of the class of the hyperbox that contains, that should be made equal to 0. Is that okay? So, accordingly, output of a compensation neuron in the containment section should go to only one class, that is the class of this particular hyperbox. It should not go to the membership function, it should not compensate the membership function of this class. Okay. So, here in the overlap compensation section, the output of this compensating neuron goes to two classes, whereas in this case the output of the containment compensation neuron will go to only one class, right. So, I get two types of compensation, one from the overlap compensation neurons and the other one for the containment compensation neurons. Now, I have to combine these two compensations. Okay. So, I have to have a combiner, right. So, over here,
sir, are you saying that the point inside the smaller hyperbox,
yeah,
that point belongs to the class of the smaller hyperbox?
yeah. that belongs to the class of the smaller hyperbox, because that defines its class membership more rigorously than the class membership of the other one. Okay. So, I will have to combine the outputs of this compensation neurons. So, I have to have a number of combiners. Okay. So, I will combine the output of this and the output of this. So, these are outputs of the output layer neurons of the compensation class belonging to the same class. Okay. So, this is class C1, this is class C1, you combine these two. Similarly, class C2, class C2, you combine these two. Okay. Finally, after combining these outputs, I know that what is the overall compensation that I have to give to the membership values generated by these neurons. These neurons are generating the membership value as if there is no containment or there is no overlap. Okay. We are trying to modify these outputs, these membership values are as computed by these compensation values. Okay. So, what I have to do is I have to add these values to these membership values, right. So, it will come over here, this will come over here, and then finally, I get the final membership value. Okay. So, you find that in case of this neural network, without any compensation section, if the membership value to a particular class, the ith class was mu I, okay. In this case, the membership value after this compensation to ith class will be mu I plus, let us put it as O I, where O I is the combination of the outputs of the overlap compensation neuron and outputs of the compensation neuron. So, over here I will have this output as O I. Okay. So, the final membership value will be mu I is what is computed by these neurons. I have to modify this with the outputs of the compensation neurons. So, the final membership value becomes mu I plus O I, and that I can take as the final membership value. So, C I to the ith class for any of the unknown feature vectors which are inputted to the neural network. Okay. So, when this compensation section neurons, whether it is overlap compensation or containment compensation, they compute the compensation values, they will make use of the same V and W matrix, the mean points and max points that we have generated for these hyperboxes. Okay. So, they will make use of the same mean point and max point to compute what should be the compensation given, and this compensation will be computed only when an unknown feature vector falls within either the overlap region or the content region. This will not be computed if the unknown feature vector falls outside the overlap region or falls outside the containment region. And when you get this, the final membership value, your classification will depend upon this final membership value. So, the classification, instead of doing based on mu I, it will be based on C I. Okay. So, in the next class, we will see the details of the membership computation or the compensation computation as done by this overlap compensation neurons and the containment compensation neurons. Okay. So, we will take the same example to design our reflex fuzzy min max neural network with, I will take the same example because I have a case of overlap, I also have a case of containment. Okay. So, with that we will illustrate that how this neural network with compensation neurons that can also be generated. Okay. So, we will stop here today. Thank you.